The next thing we're going to analyze for rational functions is end behavior. End behavior in general is what happens to the y values of our function, or what happens to our function as x goes to plus or minus infinity, or we could say as the absolute value of x gets really large. So we're looking at what happens to our function as x goes to plus or minus infinity. One type of end behavior is a horizontal asymptote. Horizontal asymptotes don't always occur. If a function has one, it will only have one. So you can only have at most one horizontal asymptote. Well, how do we describe a horizontal asymptote? If it occurs, it's a horizontal line that as x approaches positive or negative infinity, the graph is going to get closer and closer to that value, that horizontal line, but never touch it. Okay, so here I have the graph approaches but never touches as the absolute value of x gets very large. That's what goes there. It's important to note that a graph can cross a horizontal or other type of infinite asymptote, that's the end behavior, because these asymptotes describe the end behavior. That's as x goes to positive or negative infinity. So to determine if a graph crosses an infinite asymptote, which may be a horizontal, set the original equation equal to the equation for that asymptote and solve. And we're going to do this in our analysis as we go forward. So how do we find horizontal asymptotes? In general, we can find these infinite asymptotes using division, but for horizontal asymptotes, there's actually an easier way to do it. So what we're going to do is we're going to compare the degree of the numerator, which we're going to call little n, and the degree of the denominator, which we're going to call little d. Remember, the numerator and the denominator are both polynomial functions, and the degree is the highest power of x that we see in that function. So in the first case, if the degree of the numerator is less than the degree of the denominator, we're going to say it's bottom heavy. That may be something like, let's say f of x is equal to x squared plus 3x plus 7 over x to the fourth plus x cubed. Okay, the degree of the numerator here is 2. The degree of the denominator is 4. In this case, it's bottom heavy. What's going to happen is the horizontal asymptote is going to be at y equals 0. And that's because as we put larger and larger values in for x, the denominator is going to be much larger than the numerator. So we're going to have a small value in the numerator, relatively speaking, over a much larger value in the denominator, which is going to get closer and closer to 0. What happens when the degrees of the numerator and the denominator are the same? So here, the degree of the numerator is the same as the degree of the denominator. So it could be something like y equals 3x squared plus 7 over 2x squared plus x plus 9. Okay, in this case, both the degrees of the numerator and denominator are 2. In that case, we're going to have a horizontal asymptote, and its equation is going to be the ratio of the leading coefficients of the numerator and the denominator. So y is going to be equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. The numerator, remember, we're calling n of x, and the denominator we're calling d of x. So for the example that I gave right here, we will have a horizontal asymptote for this example at the ratio of the leading coefficients, which will be y equals 3 over 2. If the degree of the numerator is greater than the degree of the denominator, we're going to say that our function is top heavy. So let's say we had y equals 4x cubed plus x squared plus 7 over 2x. In this case, we're going to say the function is top heavy, and then we will not have a horizontal asymptote. And if you think about it, if we put larger and larger values in for x into the numerator, the numerator, which has that x cubed term, is going to grow much faster than the denominator that has the linear term x, which means our function, our y values, are not going to approach a constant value. It will have a different type of infinite asymptote, but it will not be horizontal. Okay, in example 5, we're going to practice finding horizontal asymptotes, doing the analysis required to find a horizontal asymptote. So here we're given a function, y equals negative 2 over x squared plus 2. So to determine horizontal asymptote, we're going to look at the degree of the numerator. In this case, the numerator is negative 2. Its degree is 0, right? Because this is like negative 2x to the 0th. The degree of the denominator is the highest power of x that we have, which is 2. So we have n equals 2 and n equals 0 and d equals 2. So we have n is less than d, right? If the degree of the numerator is less than the degree of the denominator, this is bottom heavy. And when we have a rational function that's bottom heavy, we have a horizontal asymptote at y equals 0. That's the first case we talked about. Letter B, we have 3x squared over 4x squared plus 2. The degree of the numerator is 2. The degree of the denominator is also 2. In this case, we're going to have a horizontal asymptote. It's going to be at the ratio of the leading coefficients. That's going to be the equation of the horizontal line. So the leading coefficient of the numerator is 3, right? That's the coefficient of the x squared term. The leading coefficient of the denominator is 4. So we're going to have a horizontal asymptote with the equation y equals 3/4.